Today we are going to learn about optimizing Pandas DataFrames for big data. We'll explore key strategies to efficiently manage and optimize large datasets using Pandas, enhancing your data handling skills.
Welcome to our session on optimizing Pandas DataFrames for big data. In today's data-driven world, efficiently managing large datasets is crucial. This session will equip you with the strategies needed to optimize memory usage and improve processing speeds in Pandas. As we dive into various techniques, you'll learn how to leverage data types, process data in chunks, and utilize parallel computing to enhance performance. Our goal is to transform the way you handle big data, ensuring your workflows are both efficient and effective. The first step in optimizing your Pandas data frame is understanding its memory usage. DataFrame.info is a powerful tool that provides a concise summary of your data frame, including the data types of each column and the amount of memory used. This information is crucial for identifying columns that are consuming excessive memory. By examining this output, you can pinpoint which data types might be optimized to reduce memory usage. For instance, if you have integer columns storing categorical data, converting these to category types can significantly cut down on memory consumption. Analyzing this output allows you to strategically plan your optimization process, ensuring you target the most memory-intensive parts of your data frame.
Data types play a significant role in the memory footprint of your data frame. By strategically choosing the correct data types, you can dramatically reduce memory usage. For instance, using smaller integer types like int8 instead of int64 can save memory, provided the data range fits the smaller type. Similarly, converting float types to smaller precision types can be beneficial. Another effective strategy is converting object types that store strings into categorical data types. This is especially useful for columns with repeated values. By converting these columns to categories, Pandas stores only the unique values and uses an integer array to represent the data, significantly reducing memory usage. When dealing with exceptionally large datasets, loading the entire dataset into memory might not be feasible. This is where chunking comes in. By reading data in smaller, manageable chunks, you can process large datasets without exceeding your memory limits. Pandas provides a chunk size parameter in its read functions, allowing you to specify the number of rows per chunk. Processing data in chunks involves iterating through each chunk, performing the necessary computations or transformations, and then aggregating the results. This approach not only conserves memory but also allows for more efficient processing, as you can parallelize operations across chunks if your system supports it. For large-scale data processing, leveraging parallel computing can lead to significant performance improvements. Dask is a library that extends Pandas capabilities, enabling parallel processing on large datasets. By integrating Dask with Pandas, you can distribute data across multiple cores or even different machines, thus accelerating computations. Dask data frames are designed to mimic Pandas data frames, making it easy to switch between them. This integration allows you to handle datasets that don't fit into memory by processing them in parallel, improving both speed and efficiency. Additionally, Dask handles task scheduling and optimizes computations, ensuring that resources are used effectively.
Categorical data types are a powerful tool for optimizing data frames in Pandas. These types are particularly useful when you have columns with a limited set of distinct values. By converting object types that store strings into categorical types, Pandas stores only the unique values and maps an integer to each category. This not only reduces memory usage but also speeds up operations like sorting and filtering, as comparisons are made between integers rather than strings. Implementing categorical data types is straightforward and can lead to significant performance improvements, especially in large datasets with many repeated values.
Vectorization refers to the practice of replacing explicit loops with array operations. This technique is a cornerstone of performance optimization in Pandas and other data processing libraries. Vectorized operations take advantage of low-level optimizations in NumPy, allowing for faster computations compared to traditional loops. For example, operations like addition, subtraction, and multiplication can be applied directly to entire columns or data frames without the need for iteration. This not only simplifies code but also results in substantial performance improvements, as vectorized operations are executed in optimized C code. By embracing vectorization, you can significantly enhance the speed of data processing tasks in Pandas.
To optimize effectively, it's essential to understand where your code spends the most time in memory. Profiling and benchmarking are crucial steps in the optimization process. Tools like TimeIt and Memory_Profiler allow you to measure execution time and memory usage, respectively. By analyzing these metrics, you can identify bottlenecks and areas for improvement in your Pandas workflows. Profiling provides insights into which parts of your code are inefficient, helping you focus your optimization efforts where they will have the greatest impact. By continuously benchmarking your code, you can iteratively refine your approach, ensuring optimal performance for your data processing tasks.
Handling large datasets in Pandas requires a combination of techniques and best practices. Efficient data loading is the first step. Using compression and binary formats like Parquet can significantly reduce loading times and memory usage. Balancing memory and speed is crucial. While smaller data types save memory, they may increase computation time if not chosen carefully. It's also important to continuously learn and adapt as new libraries and techniques emerge. By staying informed and flexible, you can ensure that your data handling practices are both robust and scalable, capable of meeting the demands of an ever-evolving data landscape. As we conclude our session on optimizing Pandas DataFrames for big data, let's recap the key strategies we've covered. From identifying memory usage and leveraging data types to chunking data and utilizing parallel processing with Dask, these techniques are designed to enhance your ability to handle large datasets efficiently. By optimizing your data handling processes, you can significantly improve the speed and effectiveness of your data analysis workflows. We encourage you to apply these techniques in your projects and continue exploring new advancements in the field of data optimization. Thank you for joining us, and we wish you success in your data-driven endeavors.